Scientists pointed to the most powerful telescope ever built at the deepest, most distant reaches of the universe, hoping to finally settle a nagging disagreement that had been quietly bothering cosmologists for over a decade. Instead of resolving it, the data confirmed something genuinely unsettling. The universe appears to be expanding at two different speeds, depending on how and when you measure it. Not a small rounding error, not a mistake buried in the math. A real measurable contradiction, confirmed independently by two of the most trusted telescopes humanity has ever built. We are talking about the Hubble tension, one of the most genuinely disturbing open problems in modern cosmology, and how the James Webb Space Telescope became directly involved in confirming it is real. Before you assume this means the universe is somehow broken, let's be clear about something important right away. Nobody is suggesting reality itself has stopped making sense. What they are suggesting is that our current model for describing that reality, one of the most successful scientific frameworks ever built, might be fundamentally missing something. Stick around, because this is one of the rare moments in modern physics where the deeper scientists looked, the less settled the picture actually became. Let's start with the basic concept at the center of this entire controversy, because you need to understand what the Hubble constant actually measures before you can appreciate why disagreeing about its value is such a big deal. The Hubble constant describes exactly how fast the universe is expanding, a single number that essentially tells scientists how quickly galaxies are moving away from each other as space itself stretches over time. Getting this number right is not just a minor technical detail. It directly affects our understanding of the age of the universe, its eventual fate, and the overall structure of cosmology as a scientific field. There are two fundamentally different ways scientists have historically measured this number, and that is exactly where the trouble begins. One method involves studying the cosmic microwave background, the faint, ancient radiation left over from the Big Bang, itself essentially the earliest possible snapshot of the universe. Using this method, combined with the standard cosmological model, researchers calculate a Hubble constant of roughly 67.4 kilometers per second per megaparsec. The second method involves directly measuring distances and velocities of nearby galaxies today, using specific types of stars called Cepheid, variables as reliable cosmic distance markers, then cross-referencing those measurements against exploding stars called Type Ia supernovae. This local, present-day measurement approach consistently produces a noticeably higher number, closer to 73 kilometers per second per megaparsec. Before we go further, if genuinely unresolved scientific mysteries are exactly the kind of thing that keeps you thinking long after the video ends, go ahead and tap that like button right now. It really does help this channel keep making videos exactly like this one. That gap between 67.4 and 73 might sound small on paper, but in cosmology, it represents a genuinely significant discrepancy, one that has resisted every attempt to explain it away as simple measurement error for more than a decade. Adam Rees, an astrophysicist at Johns Hopkins University, who co-received the 2011 Nobel Prize in Physics for discovering that the universe's expansion is accelerating, has led much of the research investigating this exact problem. In late 2024, Rees and his teams published a study in the Astrophysical Journal using James Webb Space Telescope data specifically to double-check earlier Hubble Space Telescope measurements, hoping to determine once and for all whether the discrepancy was a genuine feature of the universe or simply an error somewhere in Hubble's older instrumentation. The results confirmed exactly what many cosmologists had been quietly dreading. Webb's data matched Hubble's earlier measurements almost perfectly, effectively ruling out the simplest, most comfortable explanation that Hubble's telescope had simply made a subtle calibration mistake all along. According to Rees, this finding suggests that our understanding of the universe may genuinely be incomplete, a remarkably direct admission coming from one of the most respected researchers currently working in the field. If you are new here and don't enjoy watching real, ongoing scientific uncertainty get explained honestly without pretending everything has a tidy, comfortable answer, now would be a great time to hit that subscribe button, because there is a lot more of this waiting for you. So what could actually explain a genuine, confirmed difference like this? Mark Kamienkowski, a cosmologist at Johns Hopkins, who helped calculate the Hubble constant but was not directly involved in Rees's specific study, laid out several possible explanations currently being seriously considered by researchers in the field. One leading idea involves something called early dark energy, a theoretical, previously unaccounted for component of the universe that may have given cosmic expansion an unexpected boost shortly after the Big Bang, subtly throwing off calculations based on the cosmic microwave background. Other proposed explanations include unusual, poorly understood behavior in dark matter, entirely new categories of exotic particles nobody has directly detected yet, Subtle changes in the mass of electrons over cosmic history, or even primordial magnetic fields present in the very early universe that current models simply do not account for. As Kamiankowski put it, theorists currently have quite a bit of license to get creative in proposing solutions, precisely because no single explanation has yet managed to fully satisfy the data. Here is where the story takes an interesting, more hopeful turn, though, because this remains a genuinely evolving scientific debate, rather than a settled crisis. In May of 2025, a separate research team led by astronomer Wendy Friedman used a different combination of Hubble and James Webb data, arriving at a Hubble constant of 70.4 kilometers per second per megaparsec, with roughly a 3% margin of error. That figure sits considerably closer to the cosmic microwave background value of 67.4, suggesting the apparent gap between early and late universe measurements might be narrower than Rees's earlier findings had indicated, potentially even falling within the range of standard measurement uncertainty, rather than representing a genuine, unexplained physical discrepancy at all. This creates a genuinely fascinating situation, where two respected, highly experienced research teams, both using James Webb data specifically to investigate the exact same fundamental question, have arrived at meaningfully different conclusions about how serious this problem actually is. That is not a sign that something has gone wrong with the scientific process. It is exactly what genuine, unresolved scientific debate looks like while it is actually happening in real time. Rather than the neatly packaged, already settled version of science, most people only encounter well after the debate has concluded. What makes this particular disagreement matter so much, regardless of which measurement eventually proves more accurate, is what it reveals about the current limits of cosmology as a field. The standard cosmological model, technically called lambda cold dark matter, has successfully explained an enormous range of observations about the universe for decades. If the Hubble tension turns out to be a genuine confirmed discrepancy rather than a measurement artifact, it would represent one of the first to serious cracks in that otherwise remarkably successful framework, potentially forcing physicists to incorporate entirely new physics into their understanding of how the universe actually works. That is precisely why researchers describe this as genuinely disturbing in the specific, scientific sense of that word. It is not disturbing because anyone believes something dangerous or threatening is happening in the universe. It is disturbing in the way any deeply held, thoroughly tested belief becomes disturbing once solid evidence starts suggesting it might be incomplete. Physicists spent decades building confidence in the standard cosmological model specifically because it kept successfully predicting new observations before they were made. Finding a genuine, persistent gap, this significant forces a reckoning with the possibility that something fundamental about our picture of the cosmos still remains genuinely unknown. It also helps to understand exactly how scientists measure something as enormous and abstract as the expansion rate of the entire universe, because the actual technique involves a genuinely clever, multi-step process, built up over more than a century of astronomical research. Astronomers cannot simply point a telescope at the edge of the universe and read off a number. Instead, they rely on what is often called the cosmic distance ladder, a series of overlapping measurement techniques, each one calibrated against the last, allowing scientists to gradually extend accurate distance measurements from nearby objects all the way out to galaxies billions of light years away. The first rungs of that ladder rely on Cepheid variable stars, a special class of star that pulses in brightness at a very precise, predictable rate, directly tied to its true luminosity. By comparing how bright a Cepheid actually appears from Earth against how bright it should be based on its pulsing pattern, astronomers can calculate exactly how far away it sits with remarkable precision. Once calibrated using nearby Cepheids, astronomers extend that same distance ladder further out using type Ia, supernovae, a specific category of stellar explosion so consistently, predictably bright that it functions as what astronomers sometimes call a standard candle, an object whose true brightness is well enough understood that its apparent brightness alone can reveal its distance, even across vast stretches of the observable universe. Both Hubble and James Webb play a crucial role in this process, specifically because their extraordinary sensitivity allows them to detect individual Cepheid stars in galaxies far more distant than any previous generation of telescope could manage. The more distant galaxies, containing measurable Cepheids, astronomers can study, the more precisely they can calibrate the entire distance ladder, directly improving the accuracy of the resulting Hubble constant calculation. This is exactly why Webb's involvement in this research carries so much weight. Its superior infrared sensitivity allows researchers to see through interstellar dust that often obscures Cepheid measurements, taken in visible light alone, providing an independent, cleaner cross-check against Hubble's original findings. That technical detail matters enormously for understanding why Webb's confirmation of Hubble's earlier results carried so much scientific weight. If Webb's cleaner, dust-penetrating measurements had revealed a significantly different Hubble constant than Hubble's original visible light observations, it would have strongly suggested interstellar dust contamination was skewing the original results, offering a relatively straightforward, comfortable explanation for the entire tension. Instead, Webb's dust corrected. Measurements matched Hubble's original findings closely, closing off exactly that kind of simple, instrumental explanation, and leaving researchers to grapple with the more unsettling possibility that the discrepancy reflects something genuinely real about the physics of the universe itself. Both Webb and Hubble continue gathering additional data specifically aimed at narrowing down this exact question, using increasingly precise measurements of increasingly distant galaxies to refine both sides of this ongoing calculation. Researchers on both sides of the current disagreement generally agree on one point, that additional, higher precision observations remain necessary before the field can confidently declare this mystery either solved or confirmed as a genuine crack in modern cosmology. It is also worth appreciating just how significant it would be if the Hubble tension eventually proves to be a genuine, unresolved feature of the universe, rather than a measurement artifact that quietly fades away with better data. Throughout the history of physics, moments where careful, precise measurement directly contradicts an otherwise successful theoretical model have repeatedly turned out to be the exact starting point for major scientific breakthroughs. Small, persistent anomalies in planetary orbits eventually led to the development of general relativity. Unexplained gaps in atomic spectra eventually led to the development of quantum mechanics. Cosmologists studying the Hubble tension are keenly aware of this historical pattern, which is part of why so many researchers, despite understandably preferring a tidy, comfortable resolution, remain genuinely energized by the possibility that this specific discrepancy might be pointing towards similarly significant new physics. That excitement exists, alongside real scientific caution though, and it is worth understanding why so many researchers remain hesitant to declare victory in either direction just yet. Cosmology as a field has experienced false alarms before, moments where an apparently significant discrepancy in the data eventually turned out to result from an overlooked systematic error, a subtle flaw in calibration, or an incomplete understanding of some intermediate step in the measurement process. Given how much scientific weight would rest on confidently declaring a genuine break in the standard cosmological model, researchers are understandably cautious about making that declaration prematurely, preferring instead to keep gathering additional data from multiple independent teams and multiple independent measurement techniques until the picture becomes unambiguous either way. This is exactly why the disagreement between Rees's team and Friedman's team matters so much right now. Rather than representing a failure of the scientific process, having two well-respected, highly experienced groups of researchers reach meaningfully different conclusions using overlapping but distinct methodologies is precisely how genuine scientific consensus eventually gets built. Each new study, each refined technique, and each additional data point gradually narrows the range of plausible explanations, slowly converging toward an answer that the broader scientific community can eventually treat with real confidence, rather than accepting a single dramatic headline as the final word on a question this consequential. If this kind of honest, still unfolding scientific debate is exactly what you come here for, make sure you are subscribed with notifications turned on, because both Webb and Hubble continue collecting new data on this exact question. And there's a very good chance the next major study brings cosmologists significantly closer to finally understanding whether the universe is truly expanding at two different speeds, or whether this entire mystery eventually resolves into something considerably less disturbing than it currently appears. Either way, this remains one of the genuinely open frontiers of modern physics, a reminder that even our most successful, most thoroughly tested scientific models can still hide surprises once researchers look closely enough and carefully enough to notice them. Sometimes looking too deep into the universe does not hand scientists a comforting, tidy answer. Sometimes it simply hands them a better, more precisely measured version of the question, and asks them to keep looking anyway, patiently, carefully, and without any guarantee of a satisfying answer, waiting at the end of the search. Exactly the kind of quiet, disciplined uncertainty that real science is actually made of, long before any of it ever gets simplified down into a single, tidy headline.